So how many of you are familiar with what a ring is and what a field is? Speak up. Please don't type in chat. I can't check the chat.
So I just know the definition.
Okay. So just reminder, whatever you call it. Rings are where you can add and multiply. You have like the structure is closed under addition, the structure is closed under multiplication. You have something called a zero, i.e. for all elements x plus 0 is equal to x. You have something called a 1, x into 1 is equal to x for all x, and you have something called negative of a number. So you have negative 1, so that x plus minus 1 into x is equal to 0. These three things you must have. The structure must be closed under addition, the structure must be closed under multiplication. That's a ring. A field has another property that you can also divide any two numbers, and the structure is closed under division except division by 0.
Was it divide or multiply?
What?
I mean, was it divide or multiply? Like division operator comes in, multiplication.
Multiplication is already there in a ring. You can
Oh, yes,
also
yes. Yeah, divide.
divide in a field. Okay. No, I can see who raised the hand, but like I won't be able to check the meets page. So, uh, like I'm just looking at the whiteboard right now. Okay. So, and okay, of course you cannot divide by 0, but other than that you can. Simple examples of ring is the ring of integers. Rationals are also a ring, but they're also a field. What else? Z of x is a ring. U of x is a ring. That's it. Okay, so do you see why this is a ring? Uh, uh, 0, 1, 2, m minus 1 for any integer m. Like how we can define it to be a ring.
Mod M.
Perfect. This is a ring mod n. You can add, multiply, and all. Okay. So the rings we'll be looking at are commutative rings. Okay. You'll
Also
also
like Z of P, where P is a prime, it is a field, right?
you z of okay, zp. Okay.
Yes.
You mean this?
Yeah, where P is prime.
Yes, this is field. Good. Okay. One more thing is there in your rings. I'm just going to define this. Anything which has a multiplicative inverse, or like something you can divide, like if x is there and 1 by x is also there, then we call x a unit. Does this make sense?
So in rational numbers, like every number is a unit.
Yes.
Okay. So what's so special about these? Like why are we well defining this unit?
For example, if you want to talk about prime factorization in C, okay, now you can always add, multiply minus 1, 1, minus 1 in, and it's not really contributing much to what you really want to talk about, right?
Yes.
That way it's helpful to characterize units. In Z, we have -1 and 1 as units.
Oh yeah, I got it.
Oh, but like x comma 1 by x, doesn't it mean 2 and 1 by 2? And
Uh,
also,
I mean, both must be there, then X is called a unit. So if one is -1 is a unit because -1 upon -1 is also there. 1 is called a unit because 1 upon 1 is just 1, which is also there.
but like if 2 is there in a rational number field, then 1 by 2 is also there, no?
Yeah, so everything is a unit in rational numbers.
Oh, okay.
Yeah. Okay, perfect. So we have these definitions out of the way. Now what we'll be talking about are commutative rings. Can anyone guess what this means?
Rings with which like have like which are commutative. Basically, like things
Yeah,
are close.
perfect. A equal B equal B plus A B equal B A. Okay, in rings we'll also have associativity and distributivity. Okay, associativity. Okay, distributivity. You all know what these two property means. You've studied them in school. We'll also have these two properties. Okay, so now we'll look at what ideals are, which will be the main topic of what we are going to talk about today. An ideal is a part of a field, or is a part of a ring, which has some this special property. One, it's additive. Okay, like if A in the ideal and B in ideal, then so is A plus B. And if R is your ring and R is any element of the ring and A is in the ideal, then AR is also in the ideal. So it's an additive, there's additivity, and then you can scale by any element of the ring and it must still be part of the ideal. We call such structures ideals. Does the definition make sense?
So these are part of rings.
Yeah, it's a part of the ring. It's a
So
additive subgroup.
a sort of subset.
Yes.
Okay.
So can anyone give an example for ideals over Z?
I have a silly claim that if in Z, if if the ideal does not contain a negative number, then it will be infinite. Is it true?
No, I mean negative numbers have to be there. You can, if a
Yeah,
number is
negative numbers have
positive,
to be-
then you have to scale by a negative number.
So is it true?
In Z, I mean, as long as it's not the zero ideal, it has to have infinite elements in Z because you can just
Yeah.
add the maximum to or the sub add the minimum to. Yeah,
Yeah.
that's
So
kind of a claim.
like finite ideals also exist.
Yes, infinite ideals exist. Why not?
Finite.
In Z, yeah, just the zero ideal is a finite ideal.
Yeah. That's what. Yeah. Okay.
Okay, can anyone else say something? Example of an
Oh,
ideal?
even numbers is an ideal of the integers.
Perfect. In fact, for any integer m, mz is an ideal for any integer m. Okay. Come on, people, you need to speak.
Yeah, it's fine.
Yeah, okay. Cool. So, as before, as we do in real numbers, for any ideal that we have, and we have a ring, we can define something as R by I for this ideal and this ring. Now, what would you expect R by I to be? If I tell you that the Z by MZ means essentially is this ring. Any guess of how you would want to define R by I for some ring R and it and an ideal in it I, if you know that you defined usually at Z by MZ as just
Field
numbers
mod
mod M.
B. Field mod M.
What? Sorry, I didn't quite get what you said.
Field mod M.
What do you mean sealed?
Field. I mean,
What do you mean?
R minus I,
What do you mean by R minus I?
or like remove all the elements which are in I from R.
These are
I mean MZ contains 0 and you don't have M plus 1 in MZ and you don't have M plus 1 here either.
Consider the equivalence relation A is related to B if A minus B is in the ideal.
Okay,
Now quotient the ring by the equivalence relation.
perfect. That is how you do it. Like here also, that's how we defined it, right? We said A congruent to B mod M if A minus B was divisible, it was in MC. That's how we defined the congruence. And this is,
Can you repeat this part?
we say A is congruent to B mod the ideal if A minus B is in the ideal. So basically the same thing what we do mod MZ, right? Z by MZ is the same thing we do, right? We say 2M and M are equal, 2M plus 3 and 3 are equal because 2M plus 3 minus 3 is in the ideal.
Okay, so now, yeah, okay, so no, but like, did you tell the answer of this R by I thing?
That's what I'm telling. I'm not.
Sure. Okay.
You have to wait, no? So you just quotient the thing, or as Pranjal said, you quotient by the equivalence relation. So like just consider the different things that are there, uh, distinct elements A, which are not equal. So you get a bunch of equivalence classes, and you consider each of them. Okay? Does that make sense?
Yes.
Okay. So can you prove that R by I is also a ring? For any ring R and any ideal I.
I didn't get what R by I is.
So you just consider distinct elements mod I.
Oh, okay, okay.
And mod I, we say two elements are same if A congruent to B mod I. Or A minus B, sorry, we say A congruent to B mod I if A minus B is in I.
Okay.
Like it's the same idea that we always use here. Okay, so it's easy to see that it will be a ring because if you have some element A and if you have some element B, then you can define product of AB as AB mod I, and that is equal always because A plus uh, KI, it's, okay, like some element A plus K where K is in the ideal and A plus J where B plus J where B is in the here, then this is essentially what AB plus KJ plus BK plus uh, AJ. AJ is in the ideal because J is in the ideal. BK is in the ideal because K is in the ideal. KJ is in the ideal because K is in the ideal. So AB is well defined. Like it's always equal to AB if you take any element of this equivalence class mod I. Like they're all equivalent, congruent. Similarly, addition follows the same logic. Make sense?
Yes.
Perfect. So we defined division, dividing the ring by an ideal. In fact, the set of ideals is also is also rings. The set of ideals is also a ring. So how would you expect to define addition of two ideals? I is an ideal, J is an ideal. How do you want to define addition?
The union.
The union. Uh, okay, that is an interesting way to define it. I union J. Okay, cool. And how do you want to define their product? Uh, First claim we have is I union J. Any other claim? Come on, people, try to speak up.
Wait, ing are sets of numbers in ideals, or are they numbers in the ideal?
I and J are the ideals. I want to define some way of define. I want to define addition of ideals to be another ideal. How would you want to define it so that they also form a ring? Any guesses? Come on. It's not that ridiculous way of defining.
Maybe pairwise products or something. I don't know.
For which addition or uh,
Multiplication.
okay, so you have
Cross
some.
product, like the way we define cross products.
Okay, so IJ where I and I, J and J. Okay, brilliant. Can't you do addition the same way? Like simply
Yeah, I plus j where I is an I and j.
I and I, J and J.
I think I cross J can be I
So
and
to prove that something is a ring, we just have to show that it preserves all the structures.
This is ideals are not rings.
No, no, no. Like I'm asking generally.
Oh, yeah, yeah, sure. If you can prove addition is there, multiplication is, and it's a closed addition, it's closed under multiplication. Zero is there, minus one is there, associativity is there, distributivity is there. You're good. Okay, so, yeah. Okay, so why is I plus J? Is I, can you see this definition? Why is I plus J also an ideal? Anyone? Take a stab at it, take a random guess. You can say it if you know as well.
Okay, so like product of something in I plus j with some, like just write it out, it will come. Let's do
Exactly.
sum first. I1 plus j1 plus I2 plus j2 is I1 plus I2 plus j1 plus j2. So sum is fine.
Perfect.
Now I1 plus j1, sorry, I plus j into k,
Let's say R.
sure, is equal to IR plus JR, and done.
Yeah,
Then
perfect. See,
Oh, what if I plus J is not an R itself?
I plus J is not in R.
Oh, the ring.
It's a ring. It has to be there. It's the definition of a ring.
Oh, okay.
It's closed under addition.
Yeah.
Similarly, you can also show I into J is also an ideal. Because like I1, J1, I2, J2 is simply I1, I2, uh, J1, J2. Okay, you don't even need to do that in fact. You can say this is an I and this is in J. Similarly, addition is also fine. Okay.
Oh, by the way, that A union B also works, no? Like, why won't it work?
It's also, you can define it that way, but that is not actually a good definition for our purposes.
union isn't an ideal. Consider Z and consider all even numbers and things divisible by 3. That's not an ideal.
What did you say?
Like, union is not an ideal,
Yeah, okay, yeah. That's fine.
so you can't define it.
Yeah, yeah. Union does not need to be an ideal. That's fine.
Oh, ideals are sets, no? Like, union is a function. I mean, union is not a.
He's saying I union J
Oh, okay.
is not an ideal necessarily. It could be, but not necessarily. Anyway, if you define the set addition and multiplication of ideals this way, you can see they also form a ring. Can you, can anyone tell me what the zero would be in this case? The additive identity.
What about it?
What would it be?
Like what to do with this?
I mean, if you're saying that the set of ideals is also a ring, rings have zeros. What is the zero element?
Oh, the zero, the null ideal, like basically with no element.
No element, or the zero element.
Okay, yeah, zero element. Yes.
Okay. I mean, I'm not going to consider the null ideal, like the empty ideal, to be an ideal. It's not helpful for us. And what would you, sorry, what would one be?
The element with the ideal with the element one only.
Why is that an ideal? If one is there,
That may
everything.
not be there.
What?
That may not be there, right? In iCross.
What might not be there?
One.
Yeah, I in it may not be there in IJ, but like if it's the set of ideas is forming a ring, there needs to be a one, right? Like a multiplicative identity. By one, I just mean a multiplicative identity needs to be there if it's a ring.
Yeah, I meant the element one will may not be there, so the one may not be one.
Okay, I mean the entire ring itself is an ideal, right? So it can also act for purposes. It works well enough. Makes sense?
Yeah.
Oh,
Okay.
I'm not clear that how is the one the ring itself. That's it.
What exactly is the issue?
Like because so basically, if you take an ideal I and multiply by one, then it should be act with the same ideal I, right? But in that,
Oh, yeah.
then our ring contains many more elements. No.
I mean, R into I is equal to I into J for I. Whosoever that is, please mute yourself. Right? I can just. This is. Abhay, can you please see who that is? Can you kick Asmita Das Gupta from the meeting? Can you please kick Asmita Das Gupta from the meeting? Thank you. Pretty sure. I mean, they're muting and unmuting themselves, so it's okay. Thank you. J equal 1 gives you the entire ideal because J is a part of R, and it's obviously a sub ideal of, it's like a subset of I because I into J for any J is in I. So it's actually I because it has all elements of I and is a subset of I. So it is I. Okay.
I still don't get it because like it can contain elements which are not in I.
How? How?
Like the ring has elements other than the ideal also, right?
Yes, but the definition of an ideal is
Oh, okay, yes.
includes that ij must be an I
Yeah, okay, got it.
for any j in the ring. Okay, is this clear?
Yeah.
Yes.
Okay, so let us look at something called integral domains. Integral domains are things where if AB is equal to 0 implies A equals 0 or B equals 0. Make sense?
Yes.
Okay. Do you realize why some rings are not integral domains?
What did you say? Can you please repeat?
Do you realize why some rings are not integral domains?
Because they don't have zero.
All rings have zero by definition.
Oh, oops.
Can you repeat your question?
Why are some are okay? Are there even rings which are not integral domains? And a ring is called an integral domain if a b equals 0 implies a equals 0, b equals 0.
Mod P maybe.
Mod
Mod P maybe.
mod p is integral, no? Is that right?
Yeah, if
200.
one is if the
Sorry.
commutative.
Z comma Z should work, I guess.
Sure, but like
And addition and multiplication.
I mean z by 4c works. I mean
Okay, right. That's an
2
easy
into 2
example.
equals 0.
Both work, whatever.
Yeah. As Pranjal said, z into z also works for an infinite example where you define multiplication like as pairs a comma b, where a like okay, just Cartesian product. Now you can define a comma b into c comma d as the obvious thing a c comma b d and a plus c comma b plus d for addition. So this is obviously not integral because something else like 1 comma 0 into 0 comma 1 is equal to 0 comma 0. Good. Make sense?
Yes.
Okay. So this is a very important definition because we'll also like a lot of
So here A was the audit pair, right?
yes,
Okay.
because we are defining that ring that way.
Yeah, like example was clever, I think.
Yeah. So integral domains are very important. In fact, integral domains, the term can be replaced with just domains, and a lot of places only domain will be written.
Also, like complex numbers, integers, rational numbers, and like complex and reals are integral domains, right?
Yes.
Okay. Yeah.
Yes. Okay. So we often just use the term domains. Now coming back to our idea of just how we were defining the thing, how we were building things from Z, and then how we expect them to behave, like in a general ring, how we should define that thing. So in Z, we have something called primes, right? We define things called primes. How do you define primes in Z? Hello.
Which is like the number itself into the unit. It's prime factorization. Is that?
Okay, sure.
And like for absolute value, I suppose, because it's in Z.
Sure. How would you define it in an? How do you now expect to define a prime in an arbitrary ring?
Or which can be factored as only unit into that. Or like if AB equal, let I be a prime in the ring R. So if AB equal to I, then A or B should be unit.
I think definition changes in every system.
What?
of primes. I think definition of primes changes in every. Uh, wait. Nothing. Like definition remains same, but 7 may not be prime in some other system, right?
Oh, what system?
Like uh,
I'm only defining 7 to be a prime in Z.
yeah, okay.
What do you want to define a prime as?
If AB is equal to P, then A is P or B is P.
Why? I mean, in Z, you're saying if this does not mean this, right?
Like better way is A, one of A or B is a unit.
Perfect. If a number is AB, then either A is a unit or B is a unit. Brilliant. That's how you define primes, okay? Make sense? Okay, perfect. Now that you have this definition
Can
of
you wait for a moment? Okay, yes, fine.
okay, so now you define elements to be primes. Can you define what would you define want to define a prime ring as? Prime ideal as, sorry.
Also, one thing, isn't this the definition of an irreducible element and not a prime?
Uh,
I think prime was defined as if P divides AB, then P divides A or P divides B.
yes. Okay.
This is irreducible.
Okay, my bad. Yes, they're saving UFDs. Okay. My bad. So this is actually how you define end up defining an irreducible, not a prime. Okay. So stupid. I don't know what I said. Okay, what Pranjal said is correct. If P divides A, B, then P divides A or P divides B. Then P. Such things are called primes. These are prime.
That irreducible definition also works now for prime. What's wrong with that?
Yeah, it's fine, but like in Z it makes sense, right? But like in general, we these two things are not equivalent to each other.
No,
How is divisibility defined in reals or
I mean, reals, everything is a unit, so it doesn't really matter. You can divide as well. So
So do you know an example that if
in real,
A is
every element is divisible by the other, no?
yeah?
So that's perfectly fine. In reals, there's nothing to say.
So
But
we
in
right?
Z by PZ,
What?
in Z by PZ, how do you define divisibility?
Ah, Z by PZ is again what do you call it?
Field.
Field. My brain is
Oh
going
yeah,
blank.
yeah.
So it's already there. I mean, divisibility, I'm saying x divides y if there exists, if exists, are such that x are equal r. Sorry, x are equal y. My god, I'm insane today.
Okay, cool.
Yeah. Sorry, I'm being crazy today. Anyway, this is there. Now you have this definition of an irreducible and this definition of a prime. How would you want to define a prime ideal with these ideas in mind? A prime ideal you would ordinary in Z just expect to be PZ. What would you want to define it as in a general ring?
Oh, I'm not sure, but like if we consider that set of all ideals, the way we define the addition and multiplication that time, and then if then P be a,
Can we check? Can we check? Discuss that later. Like,
oh,
I
I'm defining that prime ideal only the way.
okay, sure.
And then if suppose capital P is a prime ideal and uh, ABC are other ideals, then PC equal to AB implies PC should be equal to A or PC equal to B. Like we are taking multiplication of these ideals.
Okay, sure. Any other definition?
Could you please repeat the definition of ideal?
Ideal. Okay, ideal is where you can. It's an additive subgroup, so you can add. And secondly, you should be able to multiply by any element of the ring.
So, what do you mean by prime ideal? Like a prime in an ideal ring or what?
I want you to guess what would a reasonable definition of a prime ideal be from what we know about primes in Z, or what we know how we have defined primes in R. How you would want to define a prime ideal for it to be nice to us.
Maybe P says that P divides A, B implies P divides A or P divides B.
How do you define division of rings? Sorry, division of ideals.
Like there exists some other element for which, like I say, A divides B if there exists a C such that AC equal B.
What?
Like A divides B if there is a C with AC equal B.
Hmm. But like, okay, sure. So you're saying, okay, sure. So you're saying A equal BC, then A divides B or A divides C.
Like if A says that, then maybe we can call it a prime ideal.
Sorry, but like, what the? I mean, A divide it's B or this does not make much sense, no?
Like this is not always true. For example, 6 divides 4 into 3, but 6 divides none of them individually.
6 and 4 and 3 themselves are not ideals.
Maybe it's like if AB is like in the ideal, then either A or B is in.
Perfect. That is the actual definition. Prime ideals are ideals such that AB in I implies A in I or B in I. Absolutely correct.
What was I?
The ideal. We call I a prime ideal if it satisfies this condition.
Okay.
Okay. We have also a concept of something called a maximal ideal. Can anyone guess what maximal ideal would imply?
The largest ideal that
How would you what do you mean by largest ideal?
The ring itself.
No, but like you want to have a more general concept. No, like if you're just, I'll just call it the ring itself. Why would I define a maximal ideal? I don't want it to be the ring itself. What would you want to define something which you want to call maximal? We say I is a maximal ideal. Is
Maybe if it has a maximum element.
what do you mean a maximum element? What's so like you want Z to have no maximal ideals?
Yeah, I'm not sure.
Okay, so I am telling you the definition. I is a maximal ideal if I says that I belongs to J belongs to R, then either J equal I or J equal R.
Or j equal to r.
Makes sense?
What are J and R?
J, I'm saying if there's any ideal J such that I is a subset of J and J is a subset of the ring, then either J must have been I or J must have been R. Then I say I is maximal ideal.
Then R excluding I has no ideal, right?
Then I excluding
Then R excluding the ideal has no other ideal.
uh, I if you add any more elements to the ideal, you would have to generate the entire ring is a way to put it. But I don't quite get what you mean. Okay, so a natural question is, are the concepts of prime ideal and the concept of maximal ideal equivalent?
Oh, can you give an example of a maximal ideal? If
PZ in Z.
Could you tell once again what was the ideal?
You have addition and you can scale by any element of the ring.
Okay.
oh,
It's a
for
it's a it's an additive subgroup, if that makes any sense to you. So you must have an additive inverse, you must have a zero element, and it must be closed under addition.
And that unity element?
You don't need a one because you're not multiplying.
But we if we scale them, then we are in the same set. So multiplication is there.
Multiplication is the R wala multiplication. It's not the I ka apna multiplication. You're carrying multiplication definition over from R.
Okay.
or like if I is pz, then take j as 2pz, but it is not equal to the ring. If you talk about integers,
2pz is not a subset of pz. 2pz does not include p. 2pz includes p.
you said like if but pz is a subset of 2pz, no?
No, 2pz is a subset of pz. Sorry, 2pz is a subset of pz. Pz is not a.
Oh, okay.
P is there in pz. It's not there in 2pz.
Yeah,
Any
yeah.
element of 2pz is in pz.
How do you define PZ and 2PZ?
Mz is defined as 0m minus m 2m minus 2m.
Okay.
Or better way to put it, m into z where z is in z. Okay.
Okay.
So the maximal ideal doesn't need to be have like the largest the element number of elements or something, but adding any other element should force it to become the ring itself.
Yeah, because if you want to talk about infinite ideals or infinite exit, it really does not make much sense. Talk about maximal number of elements
Yeah.
unless you're talking about some density stuff and all. That's just too messy. We want a cleaner definition, and this is a very natural definition. I don't think it's that absurd. Okay, and because you want to talk about a large class of ideals, right? Any prime, you say pz is a prime ideal. And the question is, are these two definitions equal? Are they equivalent? Like prime ideal and maximal ideal, are they equivalent? Because in Z they seem to be. Z prime ideals are pz, maximal ideals are also pz. In general, are they equivalent?
Is P always a prime or any integer?
If it was not a prime, then it does. Okay, like if you are saying mz, let p divide m, then p's mz is a part of pz, so it cannot be maximal.
Okay.
And if it has a prime factorization, okay, if m equal p q, then p and q don't need to be in mz, so it's not a prime ideal as well. It's not a prime. Yeah, so only prime ideals and maximal ideals are pz in Z. So are the definitions equivalent? It online math club does not stream the lectures, they'll upload it later.
So can we consider 1.5z like which consists of 1.53, 4.5?
It's not Z, right? Z is integers.
So I think Z by 6Z works. Consider the ideal 246. Oh, I mean 024. Oh, I was taking it as 1, 2, 3, 4, 2, 6. Can we define Z by MZ as 1, 2, 3, 4, so on till M? Like taking,
I mean, it does not make sense, right? M and 0 are the same.
yeah, so like if you take Z by 6Z and 2, 4, 6, this forms an ideal, and
Sure.
6 equal to 2 into 3, but 3 is not in this.
Okay. So
It's It's a maximal ideal, but not a prime ideal.
I mean, two is. It says A or B. It does not say A
Okay.
and B.
Yeah. Okay.
What was the example mentioned?
He said, consider 2, 4, 6 as your I and your ring as 6Z. Sorry, as Z by 6Z. He said this is a maximal ideal, but this is not prime, which is actually not correct. It is a prime ideal as well. Any guesses? Like, I'm not asking you to prove or. Uh,
Seems like it should be true so that we get some nice theorem or something. Or maybe it is true in most of the cases and not true in some very rare cases.
hmm.
Like if it is not true in general, then we don't get anything.
Yeah, yeah. So I'm asking you if they are sometimes true, or like, do you think that they are equivalent or they're different or something? Also, just one reminder that I messed up earlier. I should have mentioned this. I don't know why I messed this up earlier. The definition of IJ I messed up. IJ, sorry, I plus J is perfectly fine. The definition of IJ I messed up. IJ is not defined this way. IJ, we want it to be an ideal. So we define it as I1 J1 plus I2 J2 plus dot 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 all I k in uh, I till, okay, some I n j n I k n I j k in j and n in, sorry.
So for that maximal prime thing, I think maybe one side is true and other side is not true.
Okay, which side is your conjecture?
Maybe prime ideal is maximal ideal. Not sure. Like this is just a big guess.
Okay, since we are spending too much time on this, I'll tell you. Maximal ideals are prime ideals, but prime ideals are not necessarily maximal ideals. Can anyone prove either way? Now that I've told you this, can anyone tell me why
Could you just show once again what was prime ideal?
prime ideal is if AB in I implies A in I or B in I.
Okay.
Oh, I think I have a proof. Like, okay, suppose there is a element in the maximal ideal as AB, and both A and B are not in that the ideal.
Okay.
So we can form an ideal with the with one element A and like taking all other elements, it will contain the element AB and all the elements of that ideal. So this ideal
Why will it contain all the elements of the ideal? You said you take A and what?
AB, like AB belongs to I and A comma B doesn't belong to I. Then you form an
Okay.
ideal with the element A. Like one element is A and you form the ideal.
You mean AR, uh,
Yes.
R in R as the ideal?
Yes.
Okay, this is an ideal, but why does it need to contain all elements of I?
Uh, because like first take R as B, then AB belongs to that ideal, and now take any other element of that ring. So all the elements will be
Why? Why? Why should you be able to divide any element by A? That's basically saying that it is.
Can numbers like iota be in also the ideals?
I mean, sure, but like in Z, you're not defining it there. If you're defining the Gaussian integers or numbers of the form a plus bi, then I forms an ideal. Sure, it forms the entire ideal, but yeah, it forms an ideal for that matter.
How did we define? Oh yeah, ideal. Like is it on Z? Like we are multiplying by R while it contains numbers of Z. This is confusing.
What is the confusion? You have to explain to me the confusion, no?
Like you said, if we scale by any number in real numbers, then the new
Not
number
not
is.
reals, not reals, not reals. R is the ring. You scale by the elements of the ring.
Oh, R is not real numbers. Okay. And what is R the ring?
R is the ring.
Okay.
Ideals are part of the rings. You have an additive subgroup which is fine if you scale by elements of the ring. Which like yeah.
Okay.
This is yeah. Okay, so
Can you give
yeah,
2 minutes more just?
sure.
Oh, maybe this thing we can do, like pick all the primes in that ideal. Oh, so basically pick all the primes which are not in the ideal, but the numbers in that ideal have that in their prime factorization.
How do you define prime factorization?
Like the product of primes make that number.
Why does it need to be distinct, or why does it even need to be exist?
Okay, yes, it doesn't exist. It is not distinct in all that.
Isn't by the definition of a ring every subset of it is ideal?
How is every subset? I mean, odd numbers don't form an ideal because simply you cannot add two odds to get an odd.
Okay.
Powers of two don't form an ideal even. Yeah, like okay. Okay, so the thing is, you were almost correct. AR is good, AR is smart, but you need to add one thing. You need to consider I plus AR. Okay? This is a ring, right? J was, let's define this as J. I plus J is the ring you want to talk about. I plus J obviously includes I,
Yes.
and we have proved it's an ideal.
Why
Now,
does it include I? Like does zero in R?
0 is in J, right? Because it's an additive group. 0 has to be in R. Every ring contains the additive
Okay.
identity. Yeah, so I plus J contains I, and it must be equal to R because A is not in I, and I plus A does I plus A is also yeah is equal to R. So there is some element A, uh, R plus B is equal to 1, and similarly I plus J prime where J prime is equal to BR, R in R is also equal to R. Okay, let me say AR plus K. And similarly, BS plus L is equal to 1.
What is K?
K is some element of the ideal I. I again, L is some element of the ideal I.
And
Like
why does R include 1?
R includes 1 by definition of a ring that you need a multiplicative identity.
Okay.
Oh, by the way, why do we need this? Cannot we finish that the element B is not in I plus J, so it cannot be equal to R?
Why is B not in I plus J?
Okay, it's we are adding. So yes, B can be a plus element.
Yeah. Yeah, so AR plus K is 1, BR plus L is 1, and both are elements of I plus J and I plus J dash. Okay, so what can you say now?
Is the difference of two numbers in I again in I?
Yes, it's additive. It's an additive subgroup.
No, I am asking about difference.
Yes, yes. I mean, negatives of every number is there. So you can add the negative.
Why, like, is it a definition that 0 must be in the ideal?
A zero must be in the ideal, inverse must be in the ideal. It's an additive subgroup. Groups have inverses and identities.
From where did you learn, like, this group or subgroup, all these things? I found this really confusing.
What part is the confusion part?
No, in general, like all these groups, fields, rings, and subgroups, multiplicative group, these stuff.
Uh, Groups, where did I study from? I don't know. I actually don't remember. This I studied from Marcus number fields. Okay. So
Oh, these should be equal because there is only one.
they're equal, sure. I mean, both are one. Yeah. So they're equal, of course. You can multiply them. So 1 into 1 is equal to 1 is equal to ABRS plus ARL plus BRK plus KL. This is in the ideal I because K is in the ideal I. Again in the ideal I. L is in the ideal I, so ARL is also in the ideal I. AB is in the ideal I, so is ABRS in the ideal. So their sum is also in the ideal.
Oh, our K and L in the ideal I.
By definition of K and L, we
Like,
said
don't
I
you take
plus
K
I.
and
We said I plus J equal R. So there is some K and some AR such that AR plus K is equal to 1.
yes. So in when you are saying I, you refer to I plus J this time. I think.
No, I refer to I when I say I. I mean, the product of these two elements, I just multiplied them. I said 1
Oh,
into 1 is 1, and then I expanded it, the product.
But why is ARL and BRK in I?
Uh, L is in I, and you can scale by any element of the ring.
But A is not in I, right?
A is not in I, A is an element of the ring. It's obviously an element of the ring, right?
Oh, okay.
You can scale by elements of the ring is the point in an ideal. So BRK is also there, KL is also there, and AB is there, so ABRS is also there, so their sum is also there, which means 1 is in the ideal, which is not possible until the ideal is R itself, because 1 into R is R. You can scale by any element.
Okay.
This is a contradiction. So you get that any maximal ideal is a prime ideal.
So what if the maximal ideal is the ring itself and no other ideal exists?
Then
No
you
other.
can't define a maximal ideal if like you can't define a maximal ideal, right? Maximal ideal is an ideal which is not the ring itself, and there is no ideal between the ring and this ideal.
So,
What is going on? Even the whiteboard has a mind of its own. Amazing. Okay, so that this stuff is now there. Why are all prime ideals not maximal? If you want to look at basic algebra, I think Dummett and Foote is good.
Could you please type the thing you remember in the chat? Like,
Dummett and Foote, like just Dummett. Or if you want a basic introduction, napkin is always good. Okay, why are all prime ideals not maximal? Let's consider Zx, okay? Ring of polynomials with integer coefficients. Now, consider something such as, say, x square plus 1.
so is R equal to ZX?
R equals Zx, yes.
Okay.
Okay, so in general, I should have mentioned this for some reason I forgot. There were these ideals that we just made, right? J equal AR, such that R in R. So we have a short notation for these. We call this as this. Okay? Sorry, not AR, sorry, just A. This is, you could simply write J equal A. And it's understood what it is. Ideals of this form are called principal ideals. Okay, so you could consider anything of the form x square plus 1, let's say. Can you see why this is a prime ideal? Can you see why this is a prime ideal?
So, like, how do you remember all this? Like, do you keep revising it regularly or what?
I studied it not too long ago, and if you keep it in practice, you'll remember it. If you keep using this stuff, you'll eventually remember it. The same way you remember Olympiad stuff.
So, where do you use this stuff?
In higher mathematics problems, exercises, or the books you study from.
Oh, okay.
Okay. This stuff will, if we do some theory, if we understand some theory, you can obviously also find uses in Olympiad mathematics. Okay. But currently we're just stuck on definitions, so
Yeah, x square plus 1 is a prime ideal.
it's a prime ideal. Brilliant. Is it maximal?
What was prime ideal? Could you quickly tell?
Prime ideal is A B in I implies A in I or B in I.
Okay.
It's actually not maximal because you can consider A into x square plus 1 plus 2b, numbers of this form.
What is B? Like its range?
Uh, b is any polynomial again.
And why exactly is it prime?
This is not, I said this is prime. X square plus 1 is prime. I'm saying this is a larger ideal and it does not encompass everything
Why exactly is x squared plus 1 prime ideal?
because we know that x square plus 1 is irreducible, and if irreducible divides. I mean, if let's say your polynomial was uh, p of x in z, I x minus x, if it's in x square plus 1.
Px into x squared plus 1, right?
I mean by just the definition, it only includes elements of the form ax square plus 1. Now you're saying if I write ax square plus 1 as p into q, where p and q are uh, polynomials, where p and q are both not divisible by x square plus 1. But we know at least one of p and q has the root I, and if any number has root I, it also has any polynomial has root I, it also has root
Oh
mine.
yeah, समझ गया.
Okay, my pen is not working now for some reason. Sorry, just give me a second. Okay, great.
When you started doing this stuff, did you struggle with a lot? It with a lot because I personally struggle with it a lot. Like
I,
in
I
this
w-
class only, I forgot the definition of prime ideal 3 times.
it's fine. I was struggling with this 3 weeks ago. I still got two definitions wrong today. I got the prime definition wrong. Pranjal corrected me that I said the irreducible definition. The multiplication definition I got wrong, which I remembered later. It's fine.
Okay.
I mean, okay. More importantly, why is this not working? Suddenly, my computer's hanging now.
So, by the way, why did you take what is wait when you wrote a x square plus 1 plus 2b did you wrote
Yeah.
why 2 like why not only b?
then that encompasses everything. 2b does not encompass. If you add ax square plus 1 plus 2b, that does not encompass every element.
And why is a bracket max square plus 1 plus 2 be like not just zx?
Can you prove that? Can you see why can 1 be there?
Let me think. uh,
This is a polynomial, right?
हाँ शायद नहीं, वन तो नहीं हो सकता.
Because I mean, a is a polynomial and b is also a polynomial. You're adding two polynomials to get one, right? P of x plus q of x is equal to 1 always. So
Yeah.
p of 0 plus, sorry, p of 1 plus q of 1 is also 1.
Oh हाँ समझ गया.
That means 2a plus 2b is 1, which is not true for any polynomials a and b.
और ये सारी कंस्ट्रक्शन सोचना काफी टफ नहीं है, जैसे ये दोनों प्रूफ्स काफी इंजीनियस टाइप लग रहे हैं मतलब.
These are a bit smart, but if you're comfortable with the idea, not really.
तो ये IMOSL पे होंगे तो कम से कम N8 जैसे या N7 जैसे तो.
No, no. The thing is, like, you're not comfortable with the idea. You're not thought about the structure ever, right?
या.
इतना abstract algebra किया ही नहीं है. But someone who has thought about such a structure will find this trivial, almost. More importantly, why is my computer completely hung right now? Can you all hear me?
Yeah, we can hear you.
Okay. I cannot really control anything. Like, I cannot open any window. I cannot write anything. I'll actually have to like hard restart. That's a sad bit. Okay, I can't type now, but since you're all able to hear me, I'll conclude properly. I think a lot of the ideas here will be clear now. If you want to read more, there are a couple of resources on. If you just want to read this much, I have a blog post which I'll correct because I while explaining, I realized I had made a bunch of errors there, which I'll correct. But I have a blog post on the same. Otherwise, I have mentioned resources which are there. You can look at Ben Lin's notes. You can just Google his name and they'll come up. He has written up very nice notes. Otherwise, the book from which I'm studying myself is Marcus's Number Fields. Again, that is a brilliant book.
Could you just type the name in the chat quickly?
I can't switch windows. I can't do anything.
Uh,
I'm not able to type. I'm not able to write on my whiteboard. I'm not able to switch windows.
can you see what is being typed in the chat?
No. I'm stuck on the whiteboard. I can't do anything. I don't know what happened.
The problems are in the book, like we can find them in the book, or there are no problems with this through.
I don't intend to discuss problems. Okay, like, wait. Okay, time is also stuck on the computer. Amazing. Yeah, I don't intend to discuss any problems. If you want problems, you need a bit more theory, but you can just. I've written up claims in the blog. You can try proving each claim on your own. You can try to define stuff on your own and see if the definition matches. Right, today I tried to motivate the definition of a prime ideal, a maximal ideal. You can try to guess the definitions on your own. For some things it will make sense. Like, we have some things called Euclidean domains or unique factorization domains, principal ideal domains. You can actually guess, like, principal ideal domain and unique factorization domain. These are very guessable names.
By the way, when you are writing on whiteboard, are you just using mouse or are you using a pen?
I'm using a pen.
Oh, okay.
Is the video visible?
Yeah.
Yeah,
See.
I'm using a pen.
Because when I type using a mouse, my handwriting is very horrible.
I mean, this is also not ideal, no, like the writing I'm writing in anyway, but it's much better than I would usually get out of just a trackpad or a mouse. Anything else?
Yeah, yeah. Like suppose in OTI, suppose you ask 10 doubts, then
Uh,
approximately how much get cleared, like percentage.
I don't know. Also, this will be on YouTube, so such doubts you can ask on the server if they're not relating to.
So when will the recording be get stopped? Hi.
Abhay, are you there?
He said yes in the chat.
Okay. You can stop it whenever. I'm not going to discuss anything else anyway. Like, we
Okay.
only have 4 minutes left, and if I restart the computer and join back, it will be 8:30 by then.
So after